Okay, so we've got a lot of material to get through. First of all, one announcement, it's really a reminder. The labs will be open for you tonight, just as they've been for the rest of the conference, but there won't be evening sessions tomorrow or Friday. So there is an evening session over in the engineering workstation labs tonight. There's a lot of material in this presentation. This is really an introductory thing, very few technical details, but a lot of discussion on the kinds of things you need to think about, the questions you need to ask yourself and answer to know if putting together a Linux cluster for your research group is appropriate and what style you should do it in. It may seem at times like you're being sprayed with a fire hose, particularly since we have 3 speakers to deliver the material. The point, of course, is not for you to absorb everything, but you should clearly have been exposed to the material by the time this is done. A little bit of an outline. First of all, why you would want to buy a cluster and for what purposes is a cluster not appropriate. Various things you have to think about. And finally, some case studies on the clusters that we've put together here locally, which are appropriate for our needs and may or may not be appropriate for yours. So why clusters? Well, the main reason groups put together clusters is because they're a cheap alternative to big iron machines, complex supercomputers, big shared memory systems that cost, tens or hundreds of thousands of dollars. Some groups use them as a local development platform for programs that they eventually intend to do the production simulations on large machines such as those at NCSA or Pittsburgh, but it's nice to have your own parallel platform to do development on locally. They're very convenient because you can build the cluster to do specifically and precisely what you need to do. You don't have to spend money on capabilities that you'll never use. You can put the cluster together from COTS, which is an acronym for Commercial Off-the-Shelf Components. So it's built from parts that you can buy at any vendor, from any vendor. You run software, such as Linux and MPI libraries, for example, that you can download off the web. They're not specific to any one vendor. Your annual maintenance costs are particularly lower because whereas for a single large machine, you would want to have a service contract on that so that if it broke, you would be able to have it repaired. Whereas with a cluster, if 1 or 2 machines fail during a year, the total capability of the cluster is reduced, but it's not eliminated, so you can survive that. You don't have to put money towards a maintenance contract every year. And finally, as the machines age or as you replace them, you can redeploy them to desktops. And eventually, when they're obsolete, people feel a little bit better about getting rid of a couple of PCs that can be replaced for $500 today versus a large expensive machine that you invested a lot of money in 5 years ago. Clusters aren't for everything, of course. If your application isn't parallelizable or it's very tightly coupled, a cluster isn't going to help you. What you really need is a very fast single machine or perhaps a very fast shared memory machine to get your work done faster. If you have a large existing code base, for example, there's a group in the Beckman Institute that's put a lot of work into a DEC Fortran code that runs on their shared memory alpha servers. If the cost of porting that existing code base is too high, either for your budget or the amount of time that you have, or for the number of grad students, or for the capabilities of your grad students, then moving to a cluster may not be an option. If you don't have the source code for your application, if all you have is a commercial binary for one platform, you probably can't do that. If you have zero local expertise, so you don't know anything about Unix, you probably don't want to jump right into a cluster. You want to build up that expertise first and then reconsider. You don't have a vendor holding your hand in many cases. Of course, you can pay one of the Linux cluster vendors to put together something for you, and then you can pay them continuing support costs, but the point here is to save money, so you may not have that. And finally, if you're building a cluster from simple PCs, they're not going to have the I/O subsystem of an IBM mainframe. They're not going to have the memory capabilities of a large shared memory multiprocessor. First question that you really have to examine is, who are you building the cluster for? Who's going to use this thing? You have different situations if it's yourself and 2 grad students versus yourself and your 20 graduate students. Or if you're trying to put together a resource that's going to be used by the entire department or even the entire university. The next question, what kinds of people are these users? Well, if it's yourself and 2 grad students, possibly you don't have anyone who's clueless, competitive, or malicious. If you get up to 20 grad students, you probably will have some issues to deal with, and if it's the entire department or university, you're going to have to protect the cluster from its own users a little bit more than if it's a tightly knit group. So, as size goes up, you have issues to deal with. How are you going to allocate resources among them? 2 grad students, you can, load balance informally. 20 grad students, you might need a queuing system and some policies. Department and university, you're going to need an allocation system. What kind of existing infrastructure? Can they treat this as a standalone resource, like a supercomputing center? Or does this have to be tied into the 3 previous generations of computational equipment that's available, all running off of the same file server? And finally, if the cluster goes down, are they okay with that? Can you say, well, it's broken, I'll fix it next week, sorry? Or are people going to be screaming at you and beating on your door because they have a deadline and they were counting on this resource? So you have to think about that. And also, are you trying to get increased throughput? Do you have a large number of serial jobs that you just need to run more of at the same time? Maybe it's a standalone application. You can just run it on 50 platforms at once. You're happy. Or do you want to get one job done faster, in which case you have a small number of highly parallel jobs, and that requires a specially parallelized application like NAND, various other things. You may have to do some modifications if it's not already provided for you. As I said, the nice thing about building a cluster is you put it together for your purpose, for your application, for your users. So when you're benchmarking something, you want to look at your application, running your data set, and use that as the sole basis for deciding what to buy. And there are always trade-offs. You don't have an infinite budget, you don't have infinite space, you don't have infinite time. Your application, your users determine your choice. And even if you had all the money in the world, there are still trade-offs. There's a reason Cray is bringing back vector machines. There's a reason that NCSA has Linux clusters. There's a reason that they have big shared memory machines. And finally, I'm going to emphasize this very strongly. Do not buy the hardware until you actually have the application that you want to run on it parallelized, ported, tested, and debugged. If you want to buy 2 nodes for testing and porting, and then buy the rest of the cluster, that's reasonable. But you don't want to buy 32 machines and then say, well, during the next year, we're going to port the software to that, because a year later, you could have bought something that's 50% faster, maybe. First aspect of parallel performance is serial performance. If you can make your application run faster on a serial machine, perhaps you don't need to parallelize it at all. And also, if you're going to bother parallelizing it, you'd better put in the work to making it run as fast serially as possible. So how much memory do you need? If you're going to be thrashing, swapping to disk, then you need to invest in more memory before you spend your money on more processors. Try profiling and tuning the application. There are profiling applications which will tell you which subroutines are using the most CPU time. Focus on making that subroutine faster, optimizing it, maybe even looking for a different algorithm. Then you have to ask yourself, is this program going to be doing mostly floating point operations like matrix multiplications, or is it integer and logic? Are you working through a tree structure or comparing DNA sequences using solely the integer thing? That can affect which type of processor you decide to buy, Intel versus AMD. Is the data in cache? So you're working with a very small set, maybe half a kilobyte or half a megabyte, or Are you using, 2 gigabytes of memory, filling up all the memory on the machine, so that you're more concerned with the memory bandwidth, the bandwidth of that memory from the processor? For each time you access a piece of data, are you doing 2 operations? As in matrix multiplication, are you doing a multiply and an add and then storing it back? Or do you read data from memory, crunch on it for a long period of time before storing it? That also affects how important memory bandwidth is, the balance between Intel or AMD processors. So you have to understand the serial performance characteristics of your application, and it's actually useful to benchmark your application on different platforms. As I said, you can get small allocations of various things. If your application runs 10 times faster on an IBM P690 on one processor with enough memory as it does on a PC, well, rather than getting 10 PCs, you might not even run faster. It might be better to just go with the more expensive option, larger memory. So once you understand serial performance, if you've parallelized your application, what does it run like in parallel? How much memory do you need per node? Is it, if you run on one processor, you need 1 gigabyte of memory, but if you run on 10 processors, each processor only has 100 megabytes? Or do you need the same amount of memory on every node? How much memory is that? If you had the fastest, best balanced machine in the world so that network performance was no issue, how well would it scale? What is sort of the Amdahl's law limitation on your application? If you have a large serial component you can't avoid, maybe you can't run effectively on more than 10 nodes unless you change your algorithms drastically. And then coming back to the real world, when you're actually running on a communication network, is the scaling really affected by latency, bandwidth? What happens if you have more than one processor in a node? And finally, how fast do you actually need to run to get your science done in a timely manner? And my final slide, this is really what it all comes down to, and this is the reason that people put together clusters. You have a finite budget. What are you going to do with that? So the first thing is, how much money do you have to spend? And if you're not going to have, if you don't need a huge memory system, you don't need a very fast interconnect, don't spend your money on that. Put it where it does the most good. And also, don't solve problems you can't afford to have. If you can scale to 20 processors with, a cheap network, normal, gigabit Ethernet, or you can run on 100 processors with MirrorNet, but you can't afford 100 processors with MirrorNet, well, maybe you're stuck with, if you can afford 100 processors with the slow network, or only 20 processors with MirrorNet, but you could scale to 20 processors with gigabit Ethernet, get 3 20 processor clusters, and that's the best investment you can do. Don't try and solve a problem that you can't afford to have. And of course, one more time, don't spend any money on hardware until the application is ready. And also, make sure that the science you want to do on this cluster is ready to run before you try and put the cluster together, because otherwise you're just letting the hardware age. Tim?
Yep. Hi. Okay, my aspect as a system administrator is to keep track of the actual computational environment and the hardware choices that are specifically made. To start with, you're going to need to put your cluster somewhere. It's not going to want to go in your office. It's not going to want to go in somebody else's office. It's going to be large if it's more than 4 or 5 nodes. You need to have space, enough space to keep the fire marshals from breaking your necks. And they will break your necks if you try to stuff too many in there. I've tried. You need power and you need cooling. For space, you're going to want to rack or shelf mount all of your systems. There's no question about it. When you're getting above 4 or 5 systems, a table isn't going to cut it anymore. A 36 by 18 shelf will hold 16 PCs in a regular PC form factor. That was $180 back when we bought these things. They've got ones with wheels now. They cost a bit more. It's worth something to get those so you can move them around within the room. But be careful you don't tip anything over, because you don't want machines to crush you in the middle of the night. Multi-processor systems, if you're looking for just raw computation, putting 2 processors in the same system is probably going to help you get more compute density, which is quite important. Rack mount systems are also available. They are much smaller, but they're also much more expensive. You can expect to pay $100 for a case, or maybe $400 or $500 for a rack mount case. Power. It's not anything you really think about until it comes time to actually plug everything in usually, but then you plug 5 or 6 machines more than you were supposed to into the switch and everything blows up. We've done that lots of times too. John just did it with 2 computers the other day. A 1.3 gigahertz Athlon, which was something we used in our last cluster, draws 176 watts of power. That's more with our new systems, but I haven't measured it yet. Notice I completely ignored my own advice. A wall circuit generally provides 20 amps of power, so that means you can really run about 12 PCs on a regular circuit. If you have more than 12 PCs, and you need more than one circuit. You're also going to want to have some kind of uninterruptible power supply, a big battery. If you just buy one, you're probably going to have to work with your building people to get it actually plugged in. They run on 220 more of the time. They can usually hold, for a 5 kVA UPS, it's going to be able to hold about 24 PCs of the same wattage before. They've got bigger ones, they have smaller ones. We've tried lots of things. But if you want to save on that, you can just put your root node on the UPS. This is for one style of cluster, which will be discussed more by John in a bit. Cooling. A building air conditioner is not going to keep you cool. It's just, you try it, the machine will heat up. In our case, our machine room heats up about 1 degree a minute if you don't have air conditioning on. We turn it off for just long enough to get our work done in there because it's too cold, but then we turn it back on real quick. A single PC is going to put out about 600 BTUs of heat, and so and 1 ton of air conditioner is 12,000 BTUs. I don't really understand the tons of air conditioning thing, but that's okay. You can run about 50 PCs per ton of air conditioning, but you really want to keep that down to 30 or 40 because when you go in there yourself, you're also putting off heat and monitors and things like that. You want a margin of safety there. Hardware. There are lots of decisions to make with hardware. You want to make sure the application actually works, the users are happy with it, all the stuff that Jim talked about before. The systems integration stuff is the stuff I'm most interested in, making sure that everything's going to work together. You have computers that work, switches that work. Any one of the parts actually works together. But the most important thing is you want reliability. Having a cluster that's up half the time but is 60% of the speed of something else is still better than that full, I could have gotten something twice as fast, but it's down most of the time. So the main component of any cluster is going to be the computers. The first thing you want to do is get a demo system. Find a vendor you like, probably a local vendor, and make them build you a machine to spec. Your exact RAM you want, your exact case, your exact network card, everything that you know exactly what is in this system. You're then going to test everything on this, install Linux on it, and really beat the hell out of it. Once this all works perfectly, you buy many of that computer. Not a little bit different computer, that exact computer. The same fans on there, the same network cards. We've gotten burned by this before. Just make sure it's all exactly the same. The less changes there are later on to look at, the better off you're going to be. Having 4 or 5 different types of computers later on, you say, why did that one work and not that one? It's not worth the trouble. Also, if you plan these things right, you can later recycle them as desktops. This was discussed before. CD-ROMs and hard drives are therefore going to be a better idea in a cluster than you might think. We just got away without getting them on our last cluster, but they do generally help. But do not buy a good video card on these things. Video cards are currently advancing in technology fast enough that you'll want to buy a new one by the time you're actually recycling them. Networking. Actually, for time, I'm going to cut most of this stuff. Networking is a very important issue. You have to make sure that it can actually hold up to the kind of application you're using. The 3 main options for networking are 100 megabit Ethernet, which is fairly old. I guess it's about 10 years old now. It's cheap, $50 a node or so, including the switching. Supported everywhere, and it works quite well. It's really a good interconnect. Gigabit Ethernet has started coming into its own over the last year or 2. It's more in the range of $200 or $300 a node, and it is quite well supported, but there's less choices for good cards, and you can only get switches up to about 24 ports per switch, and there's also less opportunity to hook switches together directly. You can buy them, but you're really going from $5,000 into $20,000 for a switch at that point. There are larger interconnects if you want to make a really large network that have lower latency, higher bandwidth, all that kind of thing, like MirrorNet, but those cost more like $2,500 a node. When you're talking about a $1,000 computer, it becomes a bit of a trade-off. So we've been using gigabit Ethernet. As far as we're concerned at this point, it's the only real choice for low-cost clusters at this point. A 24-port switch lets you connect 24 nodes to it. So that's either dual processor nodes that have good 64-bit, 66 megahertz cards, or 32-bit, 33 megahertz on a single processor. Jumbo frames is interesting, but not worthy of massive discussion. For sample prices of the switches, we got the SMC Tiger switches this last time. They are slightly more powerful. They're probably worth the trouble, but the other switches will do your job just as well. The network cards have dropped very dramatically. If you can get a card for $41, don't worry too much about 100 megabit cards anymore. For other components, you want filtered power to every one of your computers. You don't want to have the possibility that some power spike is going to blow out 16 of your machines. So you can buy an isobar type thing, which we've got strewn about the room. We use these things all the time. For network cables, buy good cables. Don't just try to make them yourself. Don't try to go out and save things from your last cluster. The worst problem to bug in the world is a cable not working. You plug it in one end and you plug it in the other and it doesn't work. You see something physically there and it doesn't happen. If the cable looks bad, if you think it might be bad, if you think that in some time in the future it may go bad, if something strikes it with lightning, throw it out right away. Never let it get to the point where it can actually annoy you. If you do think this happens, you can tear them apart too. It feels good. Scissors are fun. You'll need power cables. You'll need a monitor. You probably don't want to have lots of monitors, not one per system, just one monitor to plug into each computer you're using. And you'll need video and keyboard cables, but again, very few of them, just enough to plug into the systems you need. And that's it for my part. John's up next.
So I'm going to talk a little bit about the operating system software, which is one of the other fundamental components you have to consider in building a cluster. Some of the things you have to think about: the operating system itself, message passing system, that's the software layer that allows all of the nodes in a cluster to communicate with each other. Numerical libraries, these would be things like BLAS or FFT libraries, things of that nature. Batch queuing systems, compilers that you use to actually build from source code to produce the binaries that your scientists actually run on the cluster. And then, of course, the other issues you want to keep in mind are the performance of the software and all the different layers that are involved in the cluster, the stability, because, of course, as Tim and Jim both mentioned, it's much better to have a cluster that runs at 95% of the speed that is, basically perfectly reliable than one that is 5% faster but crashes at random times. And of course, system security. One of the things that's a big issue with a cluster, the more computers you have to manage, the more effort it is. So you want to keep that in mind from the very beginning so that you don't end up having to chase down hackers who are attacking your machines in the middle of the night while you're asleep. And of course, as Jim and Tim also mentioned in some of the other talks, the software, it's a good idea to keep in mind what software already exists, the infrastructure that's in the lab or their scientists' environment already, so that the cluster fits in well with the other machines that they use. Okay, so probably the biggest thing to keep in mind, with a cluster you have a large collection of machines. So whatever you do on these machines software-wise gets multiplied by however many machines you have. So you want to use a operating system distribution that is easily cloned so that you can make one installation image and you get, through some simple process, 50 machines that are all identical. Once again, just like Tim said, you want these things to be exactly the same. If there are any differences, then if one machine malfunctions, it becomes very difficult to determine why. So you want it to be designed for this from the outset. Once again, security. Because you have a large number of machines, unlike just say your own personal desktop machine, your exposure, if you have some bug, you may have 60 machines that are just waiting to be attacked by a hacker, whereas your own desktop machine, it's a much smaller issue. So anything that you have to patch, if there's a bug in the operating system and you find out about it and there's a virus or some exploit circulating around the internet, you're going to have to apply that patch to all of the machines in the cluster. So hopefully, if you choose good software, it will be easy to do that. And once again, anything that causes trouble is multiplied by the number of nodes, so you want to make sure that you choose something that's relatively stable from the outset. Symmetric multiprocessing is an added little bit of complexity. If you go with single processor nodes, almost any of the free operating systems that are out there perform very well. Once you start having multiple processors on a motherboard, the hardware is much more complex, and thusly the system software is a lot more complicated as well. Also, the SMP support that's built into most of the free operating systems is relatively young. It's only been in the last 5 or 6 years that free software developers have had the opportunity to develop Linux kernel patches and fundamental system software like file systems, network drivers on machines of this type. And so there are a lot of extra questions you have to ask yourself. If you have a cluster built with dual processor nodes, whether or not you actually get the benefit of both of those processors has a lot to do with how the operating system actually manages those CPUs, whether or not they can both communicate equally with the network card, or if there are artificial software bottlenecks that prevent this from happening. So if your message passing system is multi-threaded, that would be an advantage. That's not the operating system itself, but if I have a better implementation of MPI, for example, it might be able to run communication threads independently of whatever the application is doing so that those things can transpire in the background while the application continues doing calculations. Another thing to keep in mind, some applications use unusual system calls, particularly applications like large memory quantum mechanical simulations. Some of them have been tuned to perform very well on data sets that are far larger than the physical memory in the computer. Something to keep in mind is whether or not those system calls scale well on a system with multiple processors. The more unusual these things are, the less likely that a lot of effort has been put into tuning those things on SMP machines. So something to be aware of. Probably more so for developers or people who have an in-house code, because you have more control over how you design the code. As far as network performance goes, you obviously want to use a distribution of Linux or another operating system where they've spent a significant amount of time optimizing the network driver performance. A lot of the latency that's in message passing systems is actually from the software layer. So to get peak performance, not only do you want a fast network card like Gigabit Ethernet or MirrorNet or something like that, but you also want to make sure that the system software that actually drives the board, the actual device drivers, are tuned and have been tested under a high load. A lot of the network drivers that are out there that work perfectly well on a desktop machine for the occasional web browser can cause serious problems in a cluster because you may have 60 machines communicating at 98% of the theoretical bandwidth that this network card is capable of, and the developer may have never tested that network driver under those conditions. So a lot of these special Linux distributions for clustering have spent a lot of time tuning those codes. Another thing, I'll skip the user space message passing for now. Unnecessary daemons. A typical Linux installation has all sorts of extra services that a person would use on a desktop machine, but they really have no purpose in a cluster. They seem innocuous at first, but if you have 1,000 machines running these little extra daemons, there's a good chance that in any one instant in time, some percentage of the machines in the cluster are, rather than running the application, your scientific code, they are off running one of these other little daemons. When this happens, if you have a collective operation like a barrier synchronization, this is particularly true of more Fortran style applications like Charm or Amber, or classically programmed MPI programs. If all the processors are expected to synchronize at some instant in time, if any of them are doing something else, that just delays all of them. And so that's something that can destroy the scalability of the cluster that is completely caused by software. User space message passing is a significant software optimization that allows your scientific application to send messages over a network card without doing what's called a context switch, which is when you switch into the operating system kernel. The advantage of it is basically you eliminate a bunch of this extra bookkeeping overhead, and the application has more control of the hardware directly. You can achieve higher peak performance, there's lower latency, and basically you cause less cache pollution so the application can run faster. There's less time spent fiddling about in the hardware. So that's something, if you have system software that can do that, that would be an advantage. So just briefly, we will show 3 slides that give you some examples of the way people physically connect and the computers to the network and how that might affect these various issues we talked about before. This is what one would call a public network. So basically, you can see the cluster on the left-hand side of the slide. It's attached to some switch, and that switch is directly attached to the rest of the world, say your regular computer network. The disadvantage to this type of architecture is those machines are directly reachable by that globe there. The globe there could also be viewed as being the hackers. So they have just as much of an ability to get to those cluster nodes as they do to your desktop machine, sending you your favorite word virus or the latest root exploit. So that's a disadvantage to this. An advantage would be if you run a lot of computational jobs. Let's say you have users that want to run MATLAB or Mathematica, and they want to be able to run the computation on a cluster node and have it display on their local desktop. This architecture allows you a lot of flexibility in that particular direction, but of course a disadvantage is the risk that you're taking with the hackers. We've had that sort of thing happen before. So, augmented is more like what NCSA does with the Platinum cluster, where you have a public network interface which is attached to the rest of the world, and you have a secondary network which is the high-performance interconnect, say MirrorNet or Quadrix or some other similar interconnect, which is private. And then all of the message passing traffic for the parallel application occurs over the secondary network. Simple things like remote file system access, running the binaries, copying data, et cetera, those things happen over the public network. And so once again, you have a lot of the advantages of the first slide, but you still have the hackers sitting there on the globe trying to get at those machines, unless you have some sort of firewall. And then the last strategy, which is actually the one that we employ in our lab, is a private network. And this is simpler for a number of reasons. You can see the cluster again on the left-hand side of the screen. The purple machine down in the lower corner of that illustration is the root node or the head node, which is the machine that drives the entire cluster. That special machine basically has 2 network interfaces, one of which is connected to the rest of the nodes in the cluster via this gigabit switch, and the other one goes to the outside world. The advantage of this strategy are twofold. One is, you can see the little picture of the globe there, the hackers have no direct route to all of those slave nodes. The only machine that they can directly attack is the purple one. So that means you have much less to worry about. They can't get at those nodes. The closest they can get is to the master node. So in a way, they're protected. It's a free firewall, if you will. Another advantage is this requires much less of your institute's IP address space. So I don't have to go talk to 15 guys across campus and request a huge number of IP addresses for this cluster. As far as we're concerned, the rest of the world need not even know that these machines are there. So it's much simpler. And just generally speaking, this one's pretty easy to manage. The disadvantage is there is no direct route for these slave nodes to get access to other external machines like this file server or your desktop computer. So if people wanted to do things like run Mathematica or MATLAB or some traditional application, there's no easy way for them to do that. And then once again, network file system access might be a big issue if you have a lot of single node jobs running on such a cluster. So, 2 of the popular Linux distributions that we have firsthand experience with here are the Skilled Beowulf distribution and Clustermatic. Both of them sort of employ this single front-end master node philosophy where there's one node that's special, which is in charge of driving the rest of those slave nodes. The root node has a full Linux installation, so it has all the standard software that you would come to expect. It has a special set of kernel patches which give you what is called a single system image. So when you run PS, for example, rather than just seeing the processes that are running on the root node, you see all the processes that are running on all of the nodes. So it makes it feel, from a user's point of view, like one giant computer rather than a discontiguous collection of machines. The other advantage to these distributions are they are sort of built from the outset so that the slave nodes have the minimum amount of exposure. They have the minimal system software. They have a fast boot time. They don't necessarily require an internal hard drive. And they have the minimal number of these various daemons, user IDs, scripts, and so on installed on each machine. So basically, this makes them very easy to manage. Installing a new compute node is maybe a 2-minute process, as opposed to the other two strategies where you have fully replicated machines or some other version like that. Once again, one disadvantage to these is that the slave nodes don't have any direct access to external file servers. So there's a way to do it, but combined with the network topology I already described, that really it's not designed for that purpose. And so the end result of that is you have extremely secure slave nodes, and then the hackers are kept at bay. So you've spent all this money on hardware. Something to keep in mind is that if you spend a lot of money on the hardware, you want to get the best sequential performance you can, serial performance, out of each of those nodes. If you were to compare a compiler like GCC on a specific platform, in this particular case, this is more applicable to, say, workstation class machines like Alphas or Suns or SGIs. Most Intel compilers are comparable or very close to the performance that GCC would produce. But on these other platforms, buying a real compiler, a commercial compiler, might give you a 3x, 2x speed increase, 20% speed increase. It just depends. Has a lot to do with the style of the code and which language. If you're running Fortran code, it's almost guaranteeable that a commercial compiler will produce much better executables than you will ever get from the free compilers. So that's something to think about. And so the moral of that story is it might behoove you to spend $2,000 on a compiler license to get 30% more performance, and that multiplied out times the number of nodes in your cluster can be very advantageous. And then, of course, you want to run your application with the compiler you're interested in, because it really doesn't matter what it runs on somebody else's benchmark. It has to be done on your actual code. Message passing libraries. Usually this is not something that you have a lot of control over unless you're the one writing the application. In NAMD's case, they use a message passing system that Sanjay Kalay's group developed, the Charm++ that you may have heard about earlier today. Other applications are typically written with libraries such as MPI, PBM, etc. You need to use a message passing system that's compatible with both the system software and the hardware that you have, as well as your application. If you can, you want to use a message passing library that provides user space message passing. Once again, it's a performance optimization. Everybody runs MPI these days. Almost any of the workstation vendors provide a free MPI implementation that comes with the machine. Certainly, all of the supercomputer centers provide MPI implementations. There are many others out there. I'll skip that because it's not so important. You'll know what you need based on what applications you want to run. So, numerical libraries. Almost any non-trivial scientific application has some need for things like BLAST libraries, linear algebra libraries, solvers of various types. It's very common that one would need some of those packages. If you put some effort into benchmarking commercial alternatives or higher performance alternatives that are platform specific, you can get a tremendous speed up over libraries like, say, numerical recipes or other commonly available packages. You're probably familiar with LinPack, LAPack, these various free packages. If you get a vendor-tuned, hand-coded assembly library for linear algebra, you can probably get a 2x or 3x speed up over doing it with your own code. So that's something to keep in mind. A big issue with a large cluster, especially the more money you spend on this hardware, the more you have to be cognizant that you want to utilize it for all that it's worth. What you can do is if you have a batch queuing system, basically that's a means of scheduling a large number of jobs to run on the hardware that's available 24 hours a day. And hopefully it can implement various policies. So as Jim said about your malevolent users or the clueless users, people that make mistakes, all that stuff. If you have a good queuing system, you can implement a lot of the policies to run your resource in the queuing system itself. So it's like the policeman. The queuing system makes sure that everybody gets a chance to run, that the jobs that are scheduled are run in a fair manner. It prevents any one individual from monopolizing the resources that are available. And it's a good way of keeping the hardware busy at all times. It basically helps you overall achieve what your goals are for the resource. Some of the trickier things with queuing systems are, if you have a large cluster, do I want to be able to run a one-node job? That's an interesting question. It actually makes it much more complicated. In our case, we have enough machines in our clusters that we just use them as a unit. So one cluster of 30 processors, we just treat it as one machine. And you either run on the whole thing or not. You can do sub-allocation of clusters, but it's much trickier, and you can have situations where there's a one-node job that's running overnight, and right behind it there's a job that wants all of the CPUs in the entire cluster. The difficulty with that is if the one-node job sits there running and running and running, the job that's waiting behind it stays there waiting all night. Meanwhile, 98% of the cluster is idle waiting for a job to fill that gap. So the nice thing about keeping it simpler and not allowing sub-allocation of clusters is it's easier to keep all of the resources busy all the time. And then there are various popular queuing systems. We use DQS. Sun Grid Engine is sort of a derivative of that. PBS you've probably used on some of the other supercomputer centers. And now we're on to the case studies.
Okay, so real quick, when we gave this talk 2 years ago, we only had one case study, and of course, since then we've recently acquired another cluster. So we're just going to run through really quick what our criteria and what our decisions were before moving on to organizing the hands-on sessions upstairs. So our group, what do we have? A lot of researchers pretty much all running the same thing, MD simulations. We have time at the supercomputer centers for the really big runs, for a lot of production, but we want to be able to get some stuff done locally. The application is NAMD almost exclusively, particularly on the clusters that we put together. Doesn't need a lot of memory, runs pretty well on Intel or AMD processors. Back in 2001, we could get 32 CPUs on fast Ethernet, and of course with the MirrorNet cluster such as NCSA, 100 CPUs and up. What was our budget? Well, we started out with something like $20,000, and various combinations of money came in slowly over time, and we eventually spent $100,000 on all of the computers that we put together, which was around 100 machines. We had a full machine room to work with, a very large UPS, which we had bought for a large SGI system that turned out to be woefully over-spec'd. And we also had an industrial air conditioner in the room, which could cool a large number of machines. What did we go with? Well, we did our benchmarking, and at the time, the fastest processor available and the fastest machine for NAMD was the Athlon 1333 megahertz processor. We went for the fastest memory that our benchmark showed, switched fast Ethernet with Intel cards, which we were happy with, and we decided to use the skilled clustering system, which was actually quite new at the time. They actually sent me email and sort of had to talk me into using it, but quite happy. Particularly, we have 3 clusters of 32 machines. One job runs on each cluster at a time. If you want to run on them, you submit your job to the queuing system, and you get to run on whatever cluster is available first for up to 24 hours. So it splits things up pretty well. Finally, we already had a queuing system, file servers, accounts set up, and Skilled was able to interoperate with that in this model. So what happened this year? Well, time goes on, processors get faster, NAMD itself gets faster. The Linux kernel runs a little bit better on those symmetric multiprocessors that John was talking about. The price of gigabit dropped, so you can get a 24-port gigabit switch for a reasonable amount of money. Machine room's starting to get full. We started noticing that there are compact form factor cases coming up, like Yay Tall from companies like Shuttle. Those are an interesting opportunity. And finally, the group is starting to emphasize, in addition to the really large simulations that we were running 2 years ago and continue to run, we want to be have even faster performance for very small interactive simulations when we want to be able to run those, now as opposed to waiting in the queue for 24 hours because you want to sit there and you want to steer it with a haptic device. So what's our budget? Well, got our money from NIH, $65,000 to spend, and eventually we scraped together some more resources. So about the same as last time. Same machine room. We can squeeze a little bit more space into our other machine room because we're retiring some obsolete machines that no one uses anymore other than John for building VMD. And the old clusters aren't obsolete yet. They're maybe only 50% slower per processor, and those are the machines you'll be working with upstairs. So we needed to compress things a little bit more, squeeze in more space. Power and cooling aren't really an option. We've got another air conditioner and 10,000 volts of power on the other side of the wall. So first option that I looked at, and I really liked this, was, well, if we get those small form factor nodes with a single processor in them, and maybe get hyper-threaded P4s, which was really, absolutely the fastest processors that we can run NAMD on using the Intel compilers today. But they only have 32-bit PCI slots, so we'd only be able to put together a 24 processor. Memory's not error correcting, it's not really server hardware, maybe not so reliable. You're only going to get maybe, half of the performance out of the gigabit network that you would want. And also, the cases are actually too small if we want to unrack them later to put the brand new fancy monitor cards in. So we rejected this, and what we finally went for were dual processor Athlons in big normal cases that'll fit the network cards. We decided to skip the hard drive or CD-ROM in the slaves and just boot them off of floppies because we realized we weren't really using the hard drive or the CD-ROM in the machines that we have now. And when we de-racked them the last time, we put DVD drives and bigger hard drives in, so what's the point? Still got to take it apart to put in the video card anyway. 24-port gigabit switch, so we can actually go up to 48 processors. Skilled hasn't released a new version in a couple of years. They've gone rather commercial, and they want like $375 per processor list price. So we went for the free equivalent from Los Alamos National Lab, booting the slaves off of floppies. We've got server-class hardware because they're dual processor machines, error-correcting memory. For those large jobs that we still run, we can use 48 processors for all of those. But for those interactive jobs, they're smaller. Maybe they only scale to 24 processors, but we can give each of those 24 processors the fastest gigabit Ethernet we can put together, and even a second processor on the node to take care of any operating system services. 36 of the old nodes are now on desktops with new video cards, RAM, hard drive, pretty cheap. We're moving the old nodes around. Right now they're upstairs waiting for you to put together some smaller clusters for smaller simulations. And the hopefully here is we still haven't worked out all of the queuing system issues to figure out how we're going to balance the load between people that want to run on the big clusters and making jobs available to run on the smaller clusters. And hopefully, economics will take over and people will decide which system is better for them. But like I said, we don't know exactly how we're going to handle that yet. And that's it. Tickets.
We have a large number of tickets. 32 people per day, just working 32 machines.
Mike.
We'll spread these out. If you want a particular session, where the sessions are right now,